So welcome to second tutorial session for the course Basic Linear Algebra. I'm Pintu Kumar. I'm a PhD scholar at IIT Bombay. Today I intend to cover just like whatever content was covered in week 2 of the course. This would be a tutorial session, so we will be discussing more and more of questions rather than looking at theory. So the topics that I intend to cover today includes system of linear equation, including rank and null space of a matrix. What do you mean by linear combinations and all? I will do many examples of vector space and subspaces, and also we'll talk about basis of a vector space and subspace. Okay, if you don't find anything clear, you can stop me at any moment. You can unmute yourself or type it in the chat box, whichever is more comfortable to you. You can ask questions both in Hindi as well as English, whatever you find more comfortable. Okay. So I have a reference book that I personally find useful for this portion of whatever I'm going to cover today. The book is called Linear Algebra, and the author for the same is Stephen H. Friedberg. I don't think the author's name is very visible from the image. I'll write it over here. It's Friedberg. You can visit chapter 1 of this if you want to study these same topics in more detail. Okay. Last time when we had session, we talked about matrix representation of system of linear equation. So our main goal was to solve a system of linear equation, and we learned how to write those system of linear equation in form of matrix representation. So today what we will try to do is we will try to generalize some of the theory around matrices so that we have better tools to solve those system of linear equation. Okay. Last time or in the first week, we covered like how do we represent a matrix in row echelon form. Okay. So just a recap, what do we do in row echelon form? We try to write matrix such that the leading so let's say this is my leading entry for my first row. So every entry below that should be 0. And the leading entry of my next row should be towards the right of this leading entry of the first row. So wherever it occurs, it should be right of this thing. Okay, so this is something that we had in row echelon form. Now, we have some notations related to this row echelon form. Let's say you are given with a matrix A and you transformed it to a row echelon form of A. Now, if you count the number of pivot elements, okay, so every pivot element will correspond to a non-zero row. So if you now count the number of pivot element, you will get something that is called as the rank of a matrix. Okay. For example, let's see this image, this example. The matrix given over here is 1, 2, 2, 1. If we do our elementary row operation, what do we need to do? We need to convert the entry before the first non-zero entry of row 1 to be 0. We want this term to be 0. How can we make it 0? So we take R2 to be R2 minus 2 times R1, right? What do we obtain? We get 1, 0, now 2 and minus 3. So 1 minus 4 gives us minus 3. So if you count the number of pivot elements now, how many pivot elements we have? 1 and 2. So rank of this matrix is 2 in this case. Okay. Similarly, for this example, let's say we have 1, 1, 2, 2. We want to make this entry as 0. Okay, so we do the same operation. R2 goes to R2 minus 2 R1. This gives us a matrix like 1, 1, 0 and 0 over here also. So if you observe that we have only one non-zero row, or in other words, we have only one pivot element. So the rank of this matrix is 1. Any doubt with how do we calculate rank of a matrix? Is it clear, like how do we calculate rank of a matrix?
Yes, sir.
Okay, thank you. So now, last time, I'm not sure you all were here or not, but we discussed to some extent how do we solve system of equations. Okay, I saw that in the course content it is covered in this week also, so I'm just giving you a ready like points that you can refer to. Okay, so let's say we have a system of equation as Ax is equal to b. Okay, so what do we mean by Ax is equal to b? Can you please turn off your audio? I'll probably. So let's say we have a matrix like yeah. So let's say we have a system of equation. Let's say like something like 2x plus 3y is equal to 4 and 5x plus y is equal to 6. Something like this we have. Okay. Then we can write it as a matrix product like this: 2, 3, 5, 1 x y is equal to 4, 6, right? So this is what you all have done in first week. So let's say we have a system of equation of form Ax is equal to b, right? And our x belongs to Rn. What do we mean by x belong to Rn is that we have n variables over here. Okay, let's say we have n variables. Then how do we check whether our system of equation have a solution or it don't have a solution? And if it does have a solution, then whether the solution is unique or like it has many solutions. Okay. So first task whenever you have a system of linear equation is to find an augmented matrix. Okay. So what you do is you write these two matrices A and B together of form 2, 3, 5, 1 and 4, 6. Okay. You write both these matrices together. Then what you do is you find the row echelon form of this matrix and then look at the rank of this matrix. Okay. Now, if rank of your augmented matrix, that is the combined matrix, is same as the rank of this A matrix, that is just this portion, and both of them is equal to n, that is your rank of augmented matrix as well as the rank of A is n, then your system has unique solution. We will have a look at some of the examples. Okay. Let's say if your rank of A augmentation with B is equal to rank of A, but this is not equal to n. Okay, that means it is less than n. Then your system has infinitely many solutions. Okay, and third case is if your rank of augmented matrix is not equal to rank of A, then your system will have no solution. Okay, so I'll take 3 examples so that it is clear that how do we solve system of equation as well as how do we look at like how many solutions we have. Okay, so we are given with this. Let's write it in matrix notation. So this is 1, 1, 1, coefficient of first equation x, y, z, and for augmented term we write 3 over here. Next row is 2, 1, 2. Next is 1, 1, 3. Okay, this is 5. This is also 5. Okay, let's try to row reduce this. What we can do as our first step is we want to make these two entries as 0. Okay, so just a second. Wait. Okay, so what we can do is we can make R3, R2 goes to R2 minus 2 times of R1, and similarly we can make R3 go to R3 minus R1. Okay, so what does this make? This makes us, this leads to 1 1 1. First row remains unchanged. Now in the second row, this terms becomes 0, minus 1, 0. Okay, this one becomes 0, 0 and 2. And this term over here becomes 5 minus 6 to be minus 1.
सर हिंदी में बोलिए.
Who was this? Do all of you understand Hindi? Then I can switch to Hindi. If there is somebody who don't understand Hindi, then it would be difficult. There is a person called Del uh, Thamarai. Do you understand Hindi? And Ravina P, do you understand Hindi? Can you write it in the chat box?
No, sir.
Then it would be difficult. If you like whoever wanted this thing to be done in Hindi, if you have any specific doubt, I can address that in Hindi. But it would be difficult to run the complete lecture in Hindi. Okay. So the third entry would be now this was R3 minus R1, which would give us 2. So now if you look at this, we wanted to find the rank of this matrix. Now you have obtained the row echelon form. So you have how many pivot elements? 3 pivot elements. So what is the rank of AB? This is 3. Okay. Now if you just look at the matrix A, that is without including the column that we obtained. Here also you obtained 3 pivot elements. So what is rank of A? Rank of A also you obtained to be 3. So both of these matches, and that is equal to the number of variables that you have. How many variables you have? 3 x, y, z. So this system has unique solution. You can also find the solution from here. So the last row would give 2z equal to 2 or z is equal to 1. And this would give minus y is equal to minus 1 or y is equal to y is equal to 1. If you put both these values in the first row, you get x plus y plus z is equal to 1, 3. That would give you x is equal to 1. So you can obtain solution also that you got unique solution. Okay. Similarly, if we look at this example, this is 1 minus 1, 1, 1, 1, 1, 1 minus 3, 1. And this is 1, 3, minus 1. Now, what we want to do is we want to make both these entries as 0. These two entries we want to make 0. How can we do that? We want to do R2 goes to R2 minus R1, R3 goes to R3 minus R1. What does this become? 1 minus 1, 1, 0, 2, 0. This one becomes 0, minus 2, and this entry is 0. Now you see both of this is a pivot element that we obtained. We want the entry below to be 0. So we do one more operation. Sorry, I forgot the column part over here. Let's include the column also. So this was 1, this would become 2, this would become minus 2. Okay. Now we want to do R3 goes to R3 minus R2. Now this is 1 minus 1, 1, 1, 0, 2. This is plus 0, 0, 0, 0, 0, 0. Now if you look at this augmented matrix, what is the this is a pivot element, this is a pivot element. The third row is completely 0, so we don't have any pivot element over here. So what is the rank of A given B? This is 2. What is rank of A. Now the matrix that you reduced is this much. You got 2 pivot element inside this also. So rank is 2. Now this is the second case, that both our rank are same, but that rank is strictly less than n. So we have infinitely many solutions over here. Okay. Similarly, you can try this example on your own, and here you will get no cell. Okay, I'll do probably quickly. 1 minus 1, 1, 1, 1, 1, 1, 3. This is 1 minus 3, 1, 2. So we want both these entries to be 0. Similar to the last time, what we will do is R3 goes to R3 minus R1, R2 goes to R2 minus R1. So we obtain 1 minus 1, 1, 1 over here. This is 0. This is minus 2, 0, 2, 0. And this is minus 2. This entry also we get as 0. And this entry we get as 1. Now you see that this is a pivot element, this entry. We want the entry just below that to be 0. 1 minus 1, 1. This is 0. Minus 2, 0. This is still over here. This is 0, 0, 0. As I'm subtracting, this is minus 1. So operation here was R3 minus R2. R3 goes to R3 minus R2. Now, if you look at the pivot elements, we have got 3 pivot elements. So rank of A augmented with B is 3. Now, if you look at just the A matrix, within A matrix, you got just 2 pivot elements. So what is rank of A? 2. So these two are not same. So the system don't have solution. Okay, so no solution. Is this thing clear to everyone? Anybody want have any doubt? जिसको हिंदी में पूछना था, if you want to ask, अगर कुछ पूछना हो तो पूछ सकते हो इधर आप, अगर नहीं समझा है तो. Okay, I'll move ahead. So when we talk about system of equations, there are two types of equation. Okay, one is called homogeneous system of equation. Second is non-homogeneous system of equation. What is the difference? So when you talk about homogeneous system of equation, we have equation of form Ax is equal to 0. So this right hand side is 0 in case of homogeneous system of equation. Okay. And this in case of non-homogeneous, this entry is non-zero. Okay, this B and B is not 0. Okay, so this is the difference between homogeneous and non-homogeneous system of equation. So when we talk about homogeneous system of equation, one thing that you should keep in mind is that this kind of system of equation always has at least one solution. So if you take all the x to be 0, okay, then this is always a solution to your system of equation. So let's say this is Ax is equal to 0. So if you put x is equal to 0, you multiply 0 with anything, what you obtain? 0. So this 0 satisfies this equation. That's why you'll always have at least one solution. Okay. Now, so you can, here in case of homogeneous system of equation, you will have only two cases. One is infinitely many solution, and one is unique solution. Okay. Now, we'll talk about something called the null space of a matrix. Okay. Now, for a matrix A, this is a set that we are defining. This is set, okay. So, this set contains all those elements which satisfy Ax is equal to 0. Okay. This set that we obtained is called the null space of a matrix A. Okay. So let's take an example and let's try to find out its null space. Okay. So our matrix that we'll obtain is 1, 1, 1, 1 minus 1, 1, 2, 0, 2. We don't have any y term over here. And our B matrix over here is 0, so we'll skip this thing and we'll not include this in augmentation. Okay. Let's try to row reduce it to echelon form. So we want to make this entry as well as this entry to be 0. So what we do? R2 goes to R2 minus R1. R3 goes to R3 minus 2R1. Okay. We obtain 1, 1, 1. This is 0, minus 2, 0. And this would become 0, minus 2, and 0. Okay. Let's make this entry also as 0 because this is our pivot element. So this becomes R3 goes to R3 minus R2. So what we obtain, this is 1, 1, 1, 0 minus 2, 0, 0, 0, 0. Okay. Now we want to write the solution for this. Okay. So let's begin from the bottom row. So the last row that we have all the entries as 0. So this what information this gives us? This gives us 0x plus 0y plus 0z is equal to 0. This does not make any sense, like this is of no use. So we'll skip this information and move to the second row. What does this say? This says that my 2 times y is equal to 0. Okay. What does this mean? This means that my y is equal to 0, right? Now let's go to the first row. What does this say? This says x plus y plus z is equal to 0. Now as my y was already 0, what does this imply? This implies that x plus z was 0. Okay. Now this is our solution space. Okay. So now as you can see, the rank of this matrix, what was the rank of this matrix? Rank of this matrix is 2. Right? You have 2 pivot elements, so the rank is 2. And how many variables we have? We have 3 variables. So our rank is not equal to number of variables. So we will have infinitely many solutions. Okay. So let's say we had z equal to s, then our x was minus s, right? So the null space of this A matrix is of form, what is it? X is, let's say, my minus s, y is always 0. If we take s, then my x became minus s for any s belonging to real number. So this set is our null space for this matrix. Is this clear to everyone? Hope this is clear. If you have any doubt, you can just ask then and there. That would be better. Okay. So this is sort of like something that you already did in first week also, sort of repetition for you. Now I'll try to cover something that is sort of new for you, so that these sessions are also fruitful for you. This is something called as linear combination. Okay. Linear combination. Let's say you have a vector v and a vector u, and let's say you have scalars c, c1, c2, this color might not be very visible, c1, c2, and so on, coming from some real numbers. Okay, so these are your real numbers c1, c2, c3, and you have two vectors v and u. Okay, what all you can do with these two vectors? You can probably add these two vectors. Okay, you can probably subtract these two vectors, or you can go one more step ahead. You can do c1 times v plus c2 times u. Okay, so something of this form is called as linear combination of u and v. Okay, linear combination of u and v. So this C1 and C2 can take any arbitrary value. So this can be -1 into v plus 1 into u, or it can be 2v minus u, anything of this form. All these combinations are called as linear combinations. Okay. Now let's talk about one more definition, then we'll go to our vector space and a lot of examples. So this is something called as linear span. So linear span is always for a set, So let's say we have a set S with vector v comma u comma w, let's say. Okay. Then span of S is defined as C1v plus C2u plus C3w, where your C1, C2 and C3 are elements of real number, are from real number. So what does this mean? Span of S is set of all possible linear combination of vectors in S. Okay. Is this are these two definitions clear to everyone? Hope this is clear. Okay. Okay. Now probably we'll do something new. Okay. So the way Sir defined vector space in class was like over the space of R, that was like quite suitable definition. But when we try to generalize it to random fields, or I would say arbitrary fields, then a proper definition of vector space comes handy. Okay. So first of all, what is a vector space? I'll try to elaborate on this. Okay. In order to make a vector space, you need 4 ingredients. Okay. First is a set called V. Okay. V is set of vectors. Okay. You need a set which contains vectors for you. Okay. Then you have another set. This is called field. If you will, like whoever is from maths background, if you will like study abstract algebra, you will know the precise definition of field. But who is not from maths department, you can see a field as something like real number or complex number, spaces like these. Okay. Real number, complex number, rational numbers. Okay. Sets like these are your fields. Okay. So you need a set called field from where you will obtain your scalars. Okay. So you want vectors, a set containing vectors. You want a set containing your scalars. And these are the 2 ingredients. Next 2 ingredients are your operations. Okay. You need 2 operations. First is your addition operation, which is defined on set of vectors. So you should know how you can add 2 vectors. Okay. This is the first thing. Second thing that you require is a dot operation or a multiplication operation. So this multiplication is not between 2 vectors. So you will not multiply 2 vectors. Rather, what you will do is you will multiply a scalar that you obtain from F. Okay. This scalar you obtained from F, and you can multiply it with some vector that you obtained from V. So you should know how to multiply these 2 things. Okay. These are the basic 4 ingredients that you need for a vector space. If it is new to you, like please ask me and stop me anywhere, like wherever you don't understand, because this is basis for linear algebra. Like this is the most basic thing that you should understand. So for a vector space, you need 4 things. First is a set of vectors. Second is a set of scalars. Third is you should know how to define addition between 2 vectors. And fourth is you should know how to define a scalar multiplication. Okay. Now, let's say you have you constructed somehow all these 4 ingredients, then these things should satisfy your these 8 properties. Okay. If it satisfies all these 8 properties, then this combination of VF, we denote it like this. Okay, this is your vector space. Okay, we'll go through the properties one by one, what it is. First is that whatever addition that you define, okay, like if you recall your real number line, you know 2 plus 3 is 5. But now you have a flexibility to define how do you want to define this addition, how you want to add two numbers or two vectors. Okay, when it comes to example, it will be more clear to you. Okay, so first thing is that this addition should be commutative. That is, your x plus y should always be equal to y plus x. Okay, we'll check it. Next is that this should be associative. Real numbers are commutative. 2 plus 3 is always equal to 3 plus 2, right? Okay. Next one is that this should be commutative. We will try to relate this to real numbers. So 2 plus 3 plus 4 is equal to 2 plus 3 plus 4. If you add 3 or 4 first, or you add 2 or 3 first, that don't make any difference, right? So that kind of property is called associative. Okay. Third property is existence of identity, that is additive identity. What does this mean is, like you should have an element denoted by 0, so that if you add it to any element in that set, any element, you should obtain the same element. So in our real number line, we have a 0, right? If you add that element to any element, this number to any element, you always obtain the same number. Let's say you add 0 to 4, or so you always obtain 4 only, or any number x plus 0, you will obtain x only. Okay. Now another thing is that you want additive inverse. Okay, so for every element x, you want a number y, so that if you add these two numbers, you will obtain 0. You want this thing to happen to you. Okay, these were the four properties related to, first four were related to addition. Okay, now we'll look two properties related to our multiplication. What does this say is that there should be an multiplicative identity, that is your element 1, so that if you multiply the 1 to any vector, you will obtain the same vector. Okay, this is one property that you must have. Next one is, like for each point, this is again like a sort of associative, that is, if you do AB into x, or you multiply this B with x first and then multiply it with A, you should obtain the same result. Okay, mind that x over here is a vector and A and B are scalar for us. Okay, these two properties are related to your multiplication. And last two properties mix both these things. These are something called as distributive properties. Okay. When we take example, I think things will be much more clearer. So this is something which is called as distributive property. So A multiplied by x plus y, you can split this bracket. So ax plus ay, and next is a plus b is ax plus bx. These things might appear very obvious for your real number line, but if you look at arbitrary spaces, this might not always be true. Okay, we'll get to examples soon. Okay, so let's take a very simple example first, then we'll gradually increase the level of examples. Okay. So what I said, we need four ingredients, that is V, F, plus and dot. We need four things to define our vector space. Let's begin with something very simple. Let's take V as R2. What is R2? R2 is R cross R. So it is a two-dimensional vector. So element would be something of form x comma y or 1 comma 2. These kind of vectors would belong to my space V or R2. Let's take my F to be real number, that is R. Okay. How would element look over here? It would look something like 1, 2, 3, minus 50, something like this. Okay. Now we want to define addition between two vectors in V. Okay, let's take the simple addition. So let's say if our u is u1 plus u1 comma u2 and v is yeah v is something like v1 comma v2, then we want to define u plus v as u1 plus v1 and second element as u2 plus v2. So we are adding the first element with first element and we are adding our second element with the second element. Okay. Now this is a pretty simple example. So let's define multiplication also. So in multiplication, what we define, c into u is equal to c times u1 into c times u2. So for example, if my u was 1 comma 2 and c was 3, then cu is equal to 3 comma 6, right? So this is how we can define our first vector space, that is called R2 over R with plus and multiplication defined above. Okay, let's check whether this is our vector space or not. Okay, so let's start with the first property, whether this is commutative or not. Okay, so if you have to check first property, so u plus v is equal to your u1 plus v1. Now, if you look at this element, just this element, this is just simple real number. Okay, and your real number elements are always commutative. So you can rewrite it as something like v2 plus, sorry, v1 plus u1 and v2 plus u2. What is this? This is v plus u. So your first property is satisfied. Okay. So this vs1, that is your commutative thing, is satisfied. Okay. Similarly, you can prove for associative. Okay. Now let's look at the existence of zero element. Okay. Second one is done. I'm assuming that. Now third one is existence of identity. So for this element, what would be our identity element? So this is 0 comma 0. So if you add 0 comma 0 to any u1 v1, sorry, yeah, u1 u2, what would it be? It would, you will again obtain u1 comma u2 only. So we have an identity element too. Okay. If you look at the fourth property, what would be the additive inverse for u1 comma u2? Additive inverse is minus u1 comma minus u2, right? This is how you can obtain. Coming to the next property, that is our fifth property, that is existence of multiplicative identity. So you can take your c is equal to 1 and this satisfies your property that 1 into any u is 1 into u1 and 1 into u2. This is same as u. Okay. And others property also follow easily for this case. Okay. So this was a very simple example. What I think that I should take a example which is not a vector space, then I think that would be more clear to you. Then we'll come back to this thing. Okay. Let's do one thing. Okay. We cover this. We don't see which property don't fail and which is not a vector space. I forgot to color this. Now we have colored this. Okay. Let's see. Again, if you look at this example, we have S to be R2. So if you look at S, so it is of form A1 comma A2. So this is something like R2 only. So we have two elements. Okay. So our V space is R2. Then we look at the next thing, that is our F space. F is your R. Now they have defined this addition and multiplication in some unique way. Okay. If you look at this multiplication, then your C times A1 comma A2 is equal to CA1 comma CA2, and which is same, right, as what we have done before. Okay. But if you look how they are adding two vectors, they have defined it differently. And they have asked us to check whether this is a vector space or not. So what they are saying is that A1 plus A2 plus B1 B2 is equal to A1 plus B1. So they are adding the first elements, and at the second position they are saying that it is A2 minus B2. Okay. Now what was our first property? First property was commutative. So if you take A plus B, this is equal to A1 A2 plus B1 B2. Okay, this we already have A1 plus B1, A2 plus A2 minus B2. Now if you take B plus A, what would you obtain? B1 B2 plus A1 A2. This is equal to B1 plus A1, and the second entry is B2 minus A2. Now if you look at this entry matches with this one, right? A1 plus B1 is always equal to B1 plus A1 for real numbers. But is it true for this entry? This is not, right? What it is asking us to show is that A2 minus B2 should be equal to B2 minus A2. Is this always true? No. So if you have A2 is equal to 2 and B2 is equal to 1, then what is A2 minus B2? This is 1 this side, and this side it would be minus 1. So this is not always true. So the example mentioned over here is not a vector space. Was this example clear to everyone? And like, I think very few of you are here. So can you please just do one thing? You can type in the chat box like what degree or what thing are you pursuing right now, so that I know like how much detail to cover and what I can just skip, so that it don't become boring for you also. Otherwise, I think I'm covering almost all the details, so it might become boring for you also. Can you please just write in the chat box what are you doing? Like what degree are you pursuing? It's bachelor's or master's, and in what subject? Okay. Others also, can you please write? Nandu and Ravina, can you please write? Ravina, then it might be a bit boring for you, but I have some proofs later on that might suit your degree. But yeah, MSc if you're doing, then this might be very basic stuff for you. Dell, this might be useful for you. Okay, I'll then try to see like whatever caters both of you. I'll take this example quickly. This is related to another set of vector space. So this kind of notation is used to represent matrices. So M n cross M means this is set of all all M cross N matrices. Okay. Now this is our V, and because I have written this R inside this bracket, okay, Nandu. So this R inside is, then F becomes a real number. Okay. Now addition operation that we have defined is same as matrix addition, and the multiplication is scalar multiplication. Okay. So if you look at these properties, whenever you are trying to prove any space as vector space, this commutative, associative, these things will mostly naturally fall, like you just need to see it once. So for example, if we look at matrix addition, then for that commutative, it is always commutative, that we already know, right? So our first property is already satisfied. It is also associative, so our second one is also true. Let's look at the third property, that what would be our zero element. So zero element in this case would be a zero matrix of size n cross m. So if you add this matrix to any matrix, then you'll obtain, let's say this is matrix A, then you'll always obtain matrix A only. Okay. So these kind of, so this 0 is our zero matrix. Now if you want to talk about inverse of this, so if you have A, if you take y, like let's say my x is A, if you take my y to be minus of A, minus of A means that every entry is multiplied by -1. Okay. So then x plus y is always 0, right? So yeah, this way you can prove that this construct that we have written is a vector space. So just for your information, that if you have set of matrices of a fixed size over a rational number or even over complex number, then it forms a vector space. So Mn cross M, let's say this over set of real numbers, again this n cross M over set of complex number, also over the set of let's say rational number, these things forms a vector space. Under what operation? Matrix addition and scalar multiplications. And scalar multiplication. Now let's take an example that is probably useful. Yeah, let's take Pn of R. This notation is known as polynomial up to degree n. Okay, this n in the denominator is polynomial up to degree n. So this set Pn, so first of all, I'm sure that all of you know what a polynomial is. Polynomial is something of form, let's say 2x square plus 3. So generalized form is summation ai x to the power I when I is equal to 0 to n. So something of this form is called polynomial. Okay. Now, so my V is this set of polynomials, that too up to degree n. So degree n or less than n. That's why my summation ran up to n. Okay. And my set of this f, that is my field, is real numbers. Okay. So now we need to define two things over here. First is your addition. Now let's say my P1 is summation I is equal to 0 to n. ai x to the power I, and my P2 is summation I is equal to 0 to n bi x to the power I. Then what is P1 plus P2? P1 plus P2. So let's say you have x plus 2, you add it to, let's say, 2x plus 1. What do? You add coefficient of x together, right? And then you add the constant terms together. So the same thing we'll do. So what we will do is, this is equal to summation I is equal to 0 to n. So we are adding the corresponding term ai plus bi. What does this mean? That we are adding a0 to b0, a1 with b1, and so on, into x to the power I. So this is how addition is defined in this case. Okay. And if you talk about multiplication, so if you multiply c p1, so this is simply defined as summation I is equal to 0 into n c into ai s to the power I. So you are multiplying this constant c along with every term in that vector. I would say like every term in the polynomial. So let's say if you are multiplying 2 with 3x square plus 1, you would have obtained 6x square plus 2, right? So you are multiplying this c with every coefficient. Okay. So now whatever I mentioned over here, this set of polynomials up to degree n and forms a vector space. And this is an important vector space. You will be using it almost everywhere. Like whatever concept you learn, you can apply it over there. Okay. Now we come to another sort of non-trivial example. Yeah. Let's say you have two fields. Right now you don't get confused between fields. You just consider this to be some non-empty sets. Okay. So let's say you have a function from S to F. Okay. So its domain is this and its range is F. Okay. And what you do, you take collection of all such functions and you write it in a set denoted by this. This is a capital F, or this you can say italic F, S to F. This denotes set of all functions from S to F. Okay, this is the notation that they are using over here. Okay, set of all functions from S to F. Two functions are called equal if like they are equal at all the points in S. So when do you call two functions equal? When the value that you obtained are same at all the points. Okay. Now this set whatever we had, along with the operation that we are given, we have to check whether this is a vector space or not. So how do we add two functions now? So let's say we have f and g. This is a new function, f plus g. If we want to obtain its value at some point s, what we do? We obtain its value at s, f plus g of s. This is how addition is defined, right? Now how do we multiply it with a scalar? Now this c of f is a new function. How do we calculate it? This is c times just f of s. First you calculate f of s, then you multiply the value with c. Okay. Right. Now we have all those are properties to satisfy. Okay. I'll go through them one by one because this is not non-trivial, but yeah, it's an interesting example. First one is commutative. So let's say my f plus g of s. What is this? F of s plus g of s, right? Now, because the domain or the range of my this function space is a field. So why did we always consider this set over which our vector space is defined as field, because we have some extra property with field, that it is always commutative and associative. So whatever properties that you are seeing for the addition, that are already satisfied for the field that you consider. Okay, so these elements, now let's say if it was real number, or because this is our field, so this is already commutative. So you can write it like this. Now because you can write it like this, you can rewrite it as like this. So these two are equal, so hence commutative. Let's go to associative. This is f plus g plus h of s. So what does this mean? F plus g of s plus h of s, and this is f of s plus g of s plus h of s. This is equal to f of s plus g plus h of s. We are just playing with definition. So this is f plus g plus h of s. So our associativity is also proved. Let's go to our third point, which is existence of identity, additive identity. Now we have to see what our identity is. So let's say our identity is denoted by I. Okay, let's say. Then what we want is that f plus I of s f plus I of s should always be wait, people are joining. Yeah, f plus I of s should always be equal to f of s. This is what we want, right? For this identity thing to satisfy, this is what we want. So let's write it as per our definition. So left hand side is f of s plus I of s. This is equal to f of s, right? So this f of s gets cancelled from the both side. We get I of s is equal to 0. So the 0 function, that is our I of s is equal to 0 everywhere, is our identity function. Okay. Now the fourth property was inverse. So again we'll denote inverse by, let's say, E. Probably not a good notation, but yeah, let's stick to it. This we want to be 0 of s or I of s. This what we want it to be I of s. This is how we solve for identity. So f of s plus E of s is equal to 0, right? I of s is 0 everywhere. So E of s is equal to minus f of s. So this is our inverse thing. Okay. The rest of the properties are not at all difficult to satisfy. Fifth one was that 1 into f should always be equal to f. So if you take this one to be the multiplicative identity of f, you are done with it. Okay. Next one was that ab into f. Now this is equal to ab into f of s. This is equal to a into b into f of s. This is ab f. This is same, right? And the distributive also you can similarly check. Now if you looked at it, Okay, so one small comment, I'll not prove this, I'll just tell you that if you look at solutions set of your like homogeneous system of equation, that is Ax is equal to 0, you look at all the x that satisfies this and you put them together in a set, then whatever set you obtained, that is also a vector space. Okay, this is just for information. But in case when your Ax is equal to b, okay, then this is not true. Okay, then this is not true. So one very important thing is that when we were doing when we were defining plus and scalar product in case of our vector space, then one important thing to keep in mind is that let's say we have v and u, whatever sum you obtain, that sum should also be in that vector space only. This is the first requirement, and the scalar product should also be in the vector space V only. This is the first and foremost requirement for a set to be vector space. Okay. So if you look at solution space, let's say Ax is equal to B. So let's say V belongs to this solution set. So AV is equal to B, and let's say U also belongs to solution set. So AU is also equal to B. Now you need to check whether V plus U belongs to your solution set or not. Okay. So if you take A of V plus U, what do you obtain? This is AV plus AU. This is equal to B plus B, which is equal to 2B. But what we wanted, that our A plus V plus U should be equal to B. So what does this mean? V does not belong to our solution space. So that's why this set that you have is not a vector space. Okay. I hope this was clear. Like if something is not clear, please stop me there or type it in the chat box. Okay. Now, if you look at this this vector space definition, you have too many properties to like check. You have 8 properties that I mentioned. Plus, you also need to verify that the u plus v thing belongs to your vector space. C dot v thing belong to your vector space. Now, in many situations, you will see that let's say you are checking, let's say you had this matrix n cross a matrix that we showed that this is a vector space. Now, if you want to look at some special kind of matrix, let's say diagonal matrices, okay. Now, if you start proving this all these properties again for the diagonal matrix, that is of no use, okay. So, because this diagonal matrix of size m cross n is a subset of your matrices of size m cross n, you can call it something like subspace, right? I'll define properly what a subspace is. Then the number of property that you have to check whether a set is a subspace of some bigger space or not is very less, okay. So let's say V of f is a vector. I'll use some other pen. I'm defining subspace over here. Let's say V of f is a vector space and W is a subset of V. Okay, we call W a subspace of V if W is a vector space under same operation. Okay, so what does this mean is that whatever subset you had, now if you want to try to satisfy all those properties on this smaller subset only, then also this property should be satisfied. Okay, if that happens, then that is called as a subspace. So if you look at this property, I'll include two more properties on the top. That is the essential, these two are essential properties. That is your, let's call it E1, that V plus U should belong to V whenever V comma U belong to V, and C dot V belongs to V whenever C belongs to your field and V belongs to V. Okay. So if you look at this property, I'll make a copy of this. Give me a minute. Okay. So what was our property E1? E1 was that V plus. Yogesh, you can ask if you want to ask anything. Okay. V plus U belongs to V, and the next is that C dot V belongs to V. Okay. This is E2. And V belongs to V. Okay. Now, let's say our W is a subset of V. Now, if you look at these properties, Vs1, Vs2, okay, and then if you look at this property, this property, this property, whichever ones I have ticked, okay, so Vs1, Vs2, Vs6. Now, see what I'm saying. I'm saying is, let's say if my X and Y belongs to W, what does this mean? That my X and Y already belongs to V, and V is satisfying all these properties. Okay. So what does that mean? That X and Y are satisfying this property, that is X plus Y is equal to Y plus X. Okay, so every element in W, because it is also an element of V, and all elements of V are already satisfying this property. So the moment we say that W is a subset of V, these 5 of our properties are already satisfied. Okay, including this Vs5 one. Okay, so these 6 properties are satisfied for us. We need to check only these 4 properties now. Okay, what does this say? That V plus U should belong to V and CV should belong to V. We can again merge them together. Let's say if we write C1 V1 plus C2, sorry, U, if this belongs to V, then we can merge these two conditions as one. This is one condition. What does this condition say? This condition say that 0 should always belong to this set, right? 0 should belong to W. This is what this condition 3 means. If we take C1 is equal to C2 is equal to 0, then this left hand side already becomes 0. So if we just write this particular property, right, this particular property, if we write, then my this property is also satisfied, this is also satisfied, this is also satisfied. And for existence of inverse, let's say if you take C1 is equal to -1, then -1 into V plus, if you take C2 is equal to 0, and 0 into V is minus of V, right? So this inverse property is also satisfied. So what does this mean? If W is a subset of V and V is already a vector space. Right? Then you just need to check this property, that is Cx plus By should belong to W. This is the only thing that you need to check for every x comma y belonging to W and C comma B belonging to scalar set. Okay. Now let's look at some of the examples. First example is the set of symmetric matrices. So we already talked about that set of n matrices of size n cross m is a vector space. Okay. Now symmetric matrices is always obviously a subset of this R set of matrices. Okay. So we just need to check this property now. Okay. So let's say x comma y belong to this S m cross n. Okay, this S m cross n I'm denoting, I'm using this to denote a set of symmetric matrices. Okay, so what does this mean? All of you know that what do we mean by symmetric matrices? Let's use bold, it would be better to denote a matrix x comma y. So symmetric matrix means that x transpose is equal to x or y transpose is equal to y. Now let's say we have some random x and y belonging to a set of symmetric matrices. What we want to show that Cx plus By is also symmetric. That is, this belongs to the set W. Okay. Let's take its transpose. Cx plus By transpose. What is this equal to? This is equal to Cx transpose plus By transpose. Now, because x is already in W, so x transpose is equal to x. This is Cx plus similarly for By. So we obtain the same thing, right? Cx plus By transpose is equal to Cx plus By. This means that Cx plus By belongs to the set W. That's why our set of symmetric matrix is also a vector space under the same operation that we talked about the set of matrices. Okay. Similarly, you can show this for diagonal matrix also. So let's say we have a diagonal matrix, let's call it Dn cross M. So if we have C times some lambda 1, lambda 2 and everything 0 plus C times let's say some B times beta 1, beta 2, 0, what is this equal to? This is equal to C lambda 1 plus B beta 1. In the next diagonal we have C lambda 2 plus B beta 2 and so on and 0 everywhere else, right? So again you can see this is also a diagonal matrix. So this is true also for diagonal matrix, that our set of diagonal matrix is a subspace. Okay, now we'll do a proof, I would say. This is a theorem, but I posed it as an example. Let's try to do this. Okay. Now, the statement is such, let's say V of f is a vector space and W1 comma W2 are two subspaces of this vector space. What can we say about W1 intersection W2? Okay, we want to check whether W1 intersection W2 is also a subspace. right? This is what we want to check. Okay. So in order to check that, what do we need to do is, let's denote this set, let's say by S. So if I have C1 S1 plus C2 S2, this should also belong to S for all S1 comma S2 in S and C1 comma C2 in field, right? This should be satisfied. Let's see how we can do. So I'll try to formally write this. Okay. Let's begin writing formally from here. Okay. Let V1 comma V2 belong to W1 intersection W2. What does this imply? And let's take constants also. C1 comma C2 belongs to F. What does this imply? That if I have V1 and V2 in intersection of two sets, then this V1 and V2 must be in both of these sets. Okay. So what does this mean? That V1 belongs to W1 and V2 belongs to W2, right? Now V2 belongs to W1 and V1 belongs to W2. So both these elements belong to both these sets, right? Now if this belongs, V1 and V2 both belongs to W1 and W1 is a subspace, then it must satisfy C1 V1 plus C2 V2 belongs to W1. Why? Because W1 is already a subspace. And the next part is C1 V1 plus C2 V2 belongs to W2. Why? Again, because W2 is already a subspace. So because now this element belongs to both these sets, then what can we infer? We can infer that C2 V2 belongs to W1 intersection W2, right? So yeah, so we just prove that the intersection of these two sets W1 intersection W2 is a subspace. Okay. We'll come to these examples a bit later. Like if time permits, we'll do this example also. But let's first solve this example 22. Let's try to solve this example 22 first. Okay. A few definitions first. So in this example, we are talking about set of functions from a set F1 to F2. Okay. So set of all functions from F1 to F2, we are talking about these functions. Okay. Now one thing is that a function is called an even function if f of minus x is equal to f of x for all x. Okay. So if this is satisfied, then your f is called as an even function. It is called as an odd function when f of minus x is equal to minus f of x. Yeah, for all x. Okay. So for example, if you take your f of x equal to x, just x, let's take x cube. Okay. Then if you put f of minus x in it, then it gives you minus x of cube, which is equal to minus x cube. So this is equal to minus of f of x, right? So your x cube is an odd function, right? And for an even function, you can take example as f of x is equal to x square. There if your minus f x, this is equal to minus x square, which is equal to x square. Okay. So this is what is defined to be an even function and an odd function. Now let's say what they have asked us to prove. Okay. So prove that set of all even function and the set of all odd function are subspaces. Okay. So we proved that the set of all functions from f1 to f2 is a vector space. Earlier we saw that. Now we want to see whether set of even function function is a subspace. This is what we have to check. Similarly, you can try for odd also. I'll prove for even function. So whenever you have to prove anything to be subspace, first step that you will take is, so let's let E denote, the E, I'm using E as a donation as set of all even functions. So we have to prove that E is a subspace, okay, of a set of all functions from F1 to F2. Okay. Now, whenever you have to prove something as subspace, first step that you should do is you should take two elements from it, E1 and E2 belonging to E. You take two elements out of it and you take two scalars belonging to the field. Okay. Now you write this thing C1 E1 plus C2 E2. Let's see, like if minus of x of this thing, if I obtain this to be the, so if I obtain f of minus x to be f of x, then a function will be an even function. What I want to show is that this complete thing, right, this complete thing over here is my even function. Okay. So let's see what we can do. So this would split as C1 E1 of minus x plus C2 E2 of minus x. So because now my E1 and E2 are already even functions, so what do we obtain? This is C1 of E1x plus C2 of E2x, right? So we can again write it similarly, C1 of E1 of plus C2 of E2x. So we obtained what we wanted, that this complete thing is an even function. So this completes the proof that set of even functions is a subspace, or you can say that it is also a vector space. Okay. So so probably I'll come to this example if time permits, but any doubt in subspace or how to prove anything as subspace? So most of you are not typing, so I'll just give you some key points. So whenever you have to, let's say, prove a W as subspace, what you should try to do is you should take two arbitrary uh, elements of W, and you should take two scalars, right, C1 and C2, and you should try to prove that C1 W1 plus C2 W2 is also an element of W. Okay. So this is what you have to do. Okay. Now we will come to basis. Okay. This was covered towards the end, Professor Rana. So we'll try to have a look at it. Okay. Just a recap, a few moments ago we talked about linear combination and spans. So I hope you remember that. Yeah. Okay. So mute this person. Oh, it's fine. So what do we mean by basis? Right now, sir has not talked about linear dependence and independence, so I won't be able to give you the precise definition for this, but I'll give you an idea like what a basis is. Okay. So let's say you have a vector space V. Okay. Now you are looking for a set B so that you can write every vector of V So let's say if you have V from here, so you can write V as some linear combination of vectors from B. Okay, you are looking something like this. Okay, so you want to write every element of your vector space V as a linear combination of elements of B. That is, span of B should be equal to your complete of V. And if you have a smaller B, right, if you have a smaller V, then you should not be able to span the complete V. If your set B satisfies these two properties, then that set B is called as a basis for that vector space B. I'll take an example. Let's say my vector space is R2 over R. So, and I choose my B to be 0, 1, comma 1, 0. Okay. Now, if I have to write 5, comma 3 in terms of this is B1, B2, how can I write 5, comma 3 in terms of B1, B2? If I take 3 times B1 plus 5 times B2, I obtain this thing. So this is 3, 5, right? So if I have any arbitrary A, comma B, I can write B times B1 plus A times B2 and I'll obtain that element. So first property is satisfied over here. What was the first property? That your span of B should be complete of V. So you can write any element of your R2 as a linear combination of these two vectors, right? So this was my first property. Second one was that if I have a smaller, let's say if I have B1 which is subset of B, then this thing should not be satisfied. Okay. So let's say you decided to remove this one. Okay. Now tell me, can I anyway write this matrix 2 comma 0 just using this B1 matrix? Like with whatever scalar I multiply it, I will never get 0 at the first position, right? So I can't write it. Similarly, if I would have removed this one, then I wouldn't be able to write, let's take different color, this one. Then I won't be able to write something like 4 comma 0. So if I remove any of these vectors from here, then I'm not able to write the other like thing. So that's why at least two elements were required over here to span my complete V. So this B was a basis for R2 over R. Okay. Basis I think would be much more clearer when sir talks about linear dependence, independence. I think that is in week 3. Now the somebody has to ask something. Mute if nobody is listening. Okay. Now, similar to as we derived for R2, let's see how we can obtain basis for Rn over R. So, the way I wrote in the above example, that is called as a standard basis for R2. So, standard basis for Rn is given by 1 0 0 0 0. So you have n such zeros, n minus 1 such zeros, and in the next one you have 1 at the second position. Okay, in the third and so on. So if you make a collection of these kind of vectors, then you obtain standard basis for this is for Rn over R. Okay. Now next thing is your polynomial space. Okay, let's say let's take an example first for this polynomial one. One thing that I want to mention, but I'm not proving it. So this basis is never unique. You can have like for the same set, you can have different bases. Okay, but the number of element in basis is always same. Okay, this is something to remember. Now let's take example of P2R. Okay, that is a set of polynomials up to degree 2. Okay, so how would a polynomial up to degree 2 look like? It would look like something like 2x square minus x plus 3, let's say, or x square plus 2x plus 4, or any this is also a member of this set. So if you want to define a basis, so that if you multiply it with some scalar and add them together, you obtain something like this, then a basis would look something like x square comma x comma 1. Okay, so this is something which is known as the standard basis for P2R. Okay, similarly for P and R, you can define standard basis to be 1 comma x square, so on till x to the power n. Okay, let's talk about a set of all matrices of size n cross m. Okay, so now what you want is that summation of all these, like if you want such vectors, so that if you sum them together multiplying with some arbitrary scalar, you should be able to obtain any matrix, right? So so a standard basis would look something like so this vectors or the elements of your basis would be matrices. So in first matrix, you have 1 at the first position and 0 everywhere else. In the second matrix, you have 0 here, 1 here, and 0 again everywhere else, and so on. So you have matrices so that you have 1, 1 at every position and 0 everywhere else. This will form a standard basis for your Mn cross M. Okay. And how many elements will be there? There would be n cross m elements. Okay. Now let's go to the question that we skipped. This was related to subspace. Okay, so these are subsets of R3, and they have asked us to check whether this is a subspace or not. Okay, let's look at the first example. What does first example say? That A1 is equal to 3 times A2 and A3 is equal to minus of A2. Okay, so again, if you want to check whether something is a subspace or not, you just need to take two elements from that set. Okay, let's take W1 comma W2 from capital W1 and take two scalars from your scalar field. So scalar over here is your real number. So let's take alpha 1 comma alpha 2 from real number. Okay, so now what you have to do is you have to take alpha 1 W1 plus alpha 2 W2 and see if this satisfies this or not.
Excuse me, sir.
Yes.
Sir, which week you explain, sir?
This is week
This
2.
week 2. Okay, okay, sir.
Yeah. So I think week 3 content is out, right?
Sir, ఇది actually మామూలుగా problem solving session is not show in this net, sir.
No. See, you won't see it as a regular video, but there would be an option to access the problem solving session.
Okay, sir.
Nandu, the problem is that we have been assigned a week late. So this week we were asked to cover week 2 only. But actually we should be covering week 3 so that uh, uh, both of us are on same page. But unfortunately we have to cover a week before this thing. Yeah. So yeah, I was talking about this set W1. We have to check whether this is a subspace or not. Okay. So we assume two elements from this set. We assume two scalars. We need to check whether this thing belongs to that set or not. Okay. Now, let's say our W1 was something like A1, A2, A3. Okay. And W2 was something like B1, B2, B3. Okay. Now, what we can do is we have to do alpha 1 W1 plus alpha 2 W2. How would the element look like now? Element would look like alpha 1 A1 plus beta, so alpha 2 B1, comma, alpha 1 A2 plus alpha 2 B2, comma, alpha 1 A3 plus alpha 2 B3. Now we need to check, let's say we call these elements as this as C1, C2 and C3. We need to check whether this C1, C2, C3 satisfies this condition that we are given. Okay. So now first condition is that A1 should be equal to 3 times A2. That is, in our notation, C1 should be equal to 3 times of C2. Okay. Now, as W1 and W2 were already elements of like this set W1, so they satisfy this property. Okay. So what is A1? A1 is 3 times A2. What is B1? B1 is 3 times B2. So if we write this again, this would be alpha times 3A2 plus alpha 1 times, this is alpha 2 times 3B2 into alpha 2. Okay. So if we take 3 common, this is alpha A2, alpha 1 A2 plus alpha 2 B2, right? So we obtained this as same as C2, right? So C1 we obtained as 3 times of C2. Similarly, we can verify this last claim also, that A3 is equal to minus A2, right? Or in our notation, this is C3 equal to minus of C2. Now, again, as W1 and W2 already are elements of this, so A3 is already equal to minus A2 and B3 is equal to minus of B2. Now we replace these values over here. We obtain C3 as my alpha 1 into minus of A2 plus alpha 2 into minus of B2. This is equal to minus alpha 1 A2, we'll take common, plus alpha 2 B2, which is equal to minus of C2. So this way we can proceed like proving any arbitrary set to be subspace. Okay. I'll take this example, B part. Okay. So B part says my W is such that A1 is equal to A3 plus 2, right? This is being satisfied by elements of like if A belongs to your W, then this is being satisfied. Again, let's take two element. Let's take U comma V belonging to W. So U would be something like U1 comma U2 comma U3, and V is something like V1 comma V2 comma V3. Now as U comma V belongs to W, so they satisfy this property, that is your U1 should be equal to U3 plus 2 and your V1 should be equal to V3 plus 2. Okay. Now let's take alpha times U plus alpha 2 times V. How would the element look? This,
Sir,
yeah.
sir, problem solving session is not mentioned. Why, sir?
So if you look at the announcements, so there are I think three TAs, we are three set of three TAs. So you can find the timing as well as the like uh, Google Meet link, like on what day would the problem solving session would be held, and using what link you can join. So you can look at the announcement. I'll share the screen if you want. Uh, if you want that information, I'll share it with you where you can find. Wait.
Actually, I am done three assignments. Some questions wrong in that's why, sir, asking how to know the solutions.
See, I'll tell you about this NPTEL courses. So whenever you submit an assignment, after let's say 1 or 2 weeks, a detailed solution for this will be uploaded. Okay, right now you don't have solution available for this, but they will upload a detailed solution for all these solutions. And after the deadline is over, let's say for this, the deadline is already over, so you can check the correct answer over here. Okay, for the detailed solution, you will have to wait for like 1 or 2 weeks. And we as a TA, if you look what we do, if you go to this announcement section, so you have this announcement. So these are the sessions that, so they post it every week. So let's say for this Tuesday, they posted that there will be a session from 6 to 8. You can join using this link. So there we try to solve a related problem to what is being taught. And you can also ask if you have any doubt. So this is how it goes.
So final exam, these models are related to exams, sir.
See, I won't say that because I am not at all related to final exam. That would be set by professor and their TA. So these questions may be related and may not be related. So we are just asked to solve problems that are related to the course content. So I can't guarantee that these kind of questions will only be asked in exam. But topics would be these only.
Okay, sir.
We try to cover a variety of questions so that we don't miss anything. But yeah, we can't guarantee that this would be the same question.
So after 2 weeks,
Mhm.
solution is there, sir. Assignment 1 and assignment 2 questions key.
They will upload. Generally, they upload after 2 weeks. They will upload soon, I guess.
Okay, sir.
Okay. So there are different TAs for different work. So we are not assigned to upload the solution. I also don't know who is assigned, but they will upload soon. Okay.
Okay, sir.
Okay. So now if we look at this example, so we need to first find alpha 1 u plus alpha 2 v. So this is something like, this is simple, like alpha 1 u1 plus alpha 2 v1 This is alpha 1 u2 plus alpha 2 v2 comma alpha 1 u3 plus alpha 2 v3. Okay. Now we need to check that whether this thing is equal to this thing plus 2. Okay. So we know value of u1 and v1, right? So let's put it over here. So the first position is alpha 1 times u3 plus 2 plus alpha 2 times v3 plus 2, right? If we just open this now, what would we obtain? This is alpha 1 u3 plus alpha 2 v3 plus 2 multiplied by alpha 1 plus alpha 2. Now, if you carefully look, what we wanted is that we just wanted a 2 over here. We didn't wanted any alpha 1 plus alpha 2 multiplied with this. We just wanted this plus 2. So let's say if you take alpha 1 and alpha 2 to be 0, okay, then what happens is that what you obtain this thing to be 0 matrix, this 0 vector, right? But now in 0 vector also you can see that this property is not satisfied, that your first element is third element plus 2. This is not satisfied. Okay. So it is not necessary for every alpha 1 and alpha 2 that this thing is satisfied. When would it be satisfied? Only when this alpha 1 plus alpha 2 is equal to 1. But our alpha 1 and alpha 2 was arbitrary. So this particular W2 is not a subspace. Okay. So any doubt in like few people are from beginning. So any doubt in whatever content that we have covered today, you can ask, or I am done with whatever I had prepared. Otherwise, we can end the session.
Sir,
Nandu, you,
yeah,
Yeah.
yeah,
you just took some 5, 6 questions together, right? Just now you answered A and B.
Yeah.
For the remaining thing, just tell us whether it is subspace or not a subspace.
Okay. So
okay, so,
You can write it down. I will take the screenshot of it.
okay. See, this one
okay,
was
see,
subspace.
this one was this.
This one was not. I'll take two colors, right? This is subspace. Okay. See, one trick is if you have these kind of equations written, and on the right hand side, if you have 0, as I said that my ax plus 0 is equal to whatever is the solution space of this thing is always a subspace, right? If you look at this first example, this was a1 is equal to 3a2. If you take 3a2 on the left hand side, so whenever you talk about something of form ax is equal to b, all the variable terms are on left hand side, right? So if you look at this, this is a1 minus 3a2 is equal to 0, and this one is a3 plus a2 is equal to 0. So your right hand side is 0 in this case. So this was your subspace, right? This is probably the trick that is being used. In the second case, if you take all the variables on the left hand side, you have some constant left on the right hand side. Okay, that's why this didn't came out to be a subspace. So your second term is, this is not a subspace. Okay, again in the third one you have this 0 on the right hand side, so this would be a subspace. Fourth one would be a subspace. Fifth one is not a subspace because again you have 1 on the right hand side. Now in the last one you have non-linear terms associated, right? You have a1, a2, a3 square. Again this one would come out to be not a subspace. You can take an example to show this, that this would come out to be not a subspace. Okay. So the answer is that A, C and D is a subspace and other three are not a subspace. Anybody else have anything? Okay, then I'll probably end this session over here. Thank you all for joining.